Okay, this is the 12.2 video. We're going to be looking at two things in this section, how to integrate vector valued functions, or they call them vector functions for short, and then also how to solve initial value problems, which is something you do more of. If I'm remembering correctly, I think it's differential equations. So here they tell you about this capital R that you're going to see in these formulas. So the capital R is just the antiderivative of the lowercase r, and the lowercase r is the vector valued function. And so down here they show you for indefinite integrals, this is page 657. For indefinite integrals, when you're integrating a vector function, you're going to get another a vector function, but then you're also going to get a plus c, which notice because it's bold is actually a vector. So it's not a constant, it's a constant vector. So if you look here in this example on the next page, excuse me, and here, the reason, hold on, I'll show you here. So what happens is in each of the integrals, because you're doing the I piece and then the j piece and then the k piece separately. So in each of the integrals, a constant comes up. And so if you then took, broke this up, so sine t in the I, c1 in the I, t in the j, c2 in the j, and then here distribute this negative t squared in the k minus c3 in the k, then this c right here, see how it's just a vector made up of constants? So it's a constant vector. So it's a little bit different. It's now a vector instead of a scalar, but it's a vector made up of scalars. So when you write it, make sure to put the hat on it. Sorry, my piece over here. Put the hat on it because it's a vector. So in the book they make it bold, but when you write it in your notes, you'll need to put the hat on it. Okay, if it's a definite integral, it does not need a plus c. And again, you're just looking at each of the pieces separately, like it's three separate problems, and then it's going to come out as a vector. And they talk here about it from Fundamental Theorem of Calculus. This is Fundamental Theorem of Calculus Part 2 that this comes from. So again, the capital R is the antiderivative of the lowercase r. All right, and then we're not going to do this, but for those of you whose field is physics related, so if your major has anything to do with physics, they talk on page 659. Here it starts talking about, in physics, projectile motion. So we're going to skip that here. But if your field is heavy in physics, or you need to know how to do projectile motion, that starts at the kind of the middle here of page 659 and continues all the way through to the end of 661. So we're not going to do that in calculus, but in case you need it for physics, definitely take some time to read that. All right, we're going to look at some examples. Well, actually, first let me show you my notes. So here's kind of the stuff, pretty much exactly what was in the book. Sometimes I write it differently, but pretty much the same. So here the capital R is the antiderivative. When you integrate an indefinite integral, you need plus c. Notice here I'm putting it with a hat instead of bold. Example 1 talks about what the c is. Definite integrals by either one of these. All right, now let's look at some examples. So 1 through 10, evaluate the integral as the directions. So again, what you're going to do is do each piece separately and keep them separated from each other. So like here, this is the I piece, this is the j piece, this is the k piece. Notice this is t to the -2. This was t to the 1/2. And then when you integrate, again, because you have to keep the ij's and k separately, or keep the pieces separate. So for the I piece, here's where I plug in the 2, and then here's where I plug in the 1, and that's for the I. And then 2 and 1 for the j, 2 and 1 for the k. So you can't combine pieces from here with pieces from here. So you need to do, take care of both parts of the I, both parts of the j, both parts of the k, like that. And then when you simplify it down on a definite integral, it's still going to be a vector, but it's going to be a vector whose components are all scalars or numbers, right? So not functions. I shouldn't say scalars, but they're not functions. They're just constants. Okay, so let's look at another one. This one's slightly more complicated. Number 8, same idea. You're going to keep all the pieces separate, but notice this piece and this piece, unless you just have them memorized, you can't integrate them like regular. They both need integration by parts. And so I'm just going to come over here and do them each separately and then put them all back together. So here for this one, this is the integration by parts. Integration by parts is an 8.1. So if you need to review integration by parts, go back to 8.1 and you can review that. But here's the pieces. So I integrate it and I get this. And then for this one, here's the pieces. Integrate it and get this. So if you're unfamiliar with integration by parts, you might want to pause the video and try both of those to make sure you remember how to do it. And so this was my original problem. This was what I had to start with. And then this became these two pieces, see right here. And then this became those two pieces. So I've got this. So notice my I piece became this after I integrated. k piece became this after I integrated. It looks like I didn't do anything with my j, but when you integrate e to the t, it's still just e to the t. So I did integrate it, but it doesn't look like it. And then again, when you plug in, plug in ln of 3, and then 1 for the I, and then here for the j, then here from the k. And then you're just simplifying, so this is a lot of mess. The k piece looks dreadful, but that's really all you can do in terms of simplifying it. So that would be number 8. So some of them are going to require u substitutions. Some of them are going to require integration by parts. Some of them are going to be just basic. But again, you're just taking it one piece at a time and then putting it all together as a vector for your answer. Okay, so initial value problems. You did this in Calais. I don't think they called them initial value problems, but here it says solve for R. So R is the position vector. And so they're either going to give you like 12 through 14. They're either going to give you the first derivative of R and one extra piece of information, or like 15 and 16, they're going to give you the second derivative of R and then 2 extra pieces of information. So for every time you have to integrate, you need another piece of information, because what you're doing here basically is finding the C, the constant. Okay, so number 12, they just gave you the first derivative. So this is my first derivative and then one extra piece of information. So the original function is the integral of the derivative, because the integral of the derivative cancels out, just gives you back the original function. So I'm integrating the derivative, so I put that here. And then when I integrate, I get plus c. Okay? Then, according to this, if I plug in a 0, it should be equal to 100j. So I go here, and everywhere I have a t, I plug in a 0. So r of 0 is this. And then, according to this up here, that should be equal to 100j. So I set it equal to 100j. So notice it's 0 in the I, 0 in the j, and then plus c. So my c must be equal to 100j. So because that's in the j part, I go back in up here, and I plug it in with the j. And so it didn't have any i's to it, so I didn't plug in with the i's, but I put it here with the j. Okay, so that would be my r. So your final answer on these should be r equals, and then this vector value function. So you plug in the c. Don't just stop when you find the c, plug it in. All right, so that's what you do if you just have the first derivative. Now let's look at what you would do if you have the second derivative. So this is number 16. So notice here it's the second derivative. So this is like acceleration, right? The first derivative, velocity, second derivative, acceleration. Oh, before I forget, hold on. I'm having to remake this video. I made it originally over the summer, and I was using the same video sheet from over the summer, but I couldn't get it to, long story short, it wouldn't work. So I'm having to redo it. But I need to tell you some of these answers to see if you were paying attention. So for number 5, for my random story to see if you were paying attention, what was special about the day I recorded the video? Nothing special about today, but the day I recorded the video originally in the summer was my wedding anniversary. So it was my wedding anniversary. And then for number 7, I have been married 17 years. That's probably about as long as some of you have been alive. That makes me feel really old. Whatever, 17 years is the answer to number 7. I'll tell you the answer to number 6 later, because that's about some pets that I don't even have anymore, so whatever. Anyway, back to this problem. Here's the second derivative. They gave you 2 pieces of information. Notice this is just a weird way of saying the value of the derivative at 0. So they could have written, hold on, let me write it. They could have written it, I can't write and look at the same time, so give me just a second. Okay, they could have written it like this. This is a weird way to write this. All right, now let's look at this. So the first derivative is the integral of the second derivative. So here's my second derivative. So this is what I'm integrating. These are just 1s, so they would just become t's. And then because I'm going to have 2 different constants, I'm calling this C1, okay, to not confuse it with C2. So this is C1. And then this is telling me into my first derivative, if I plug in a 0, it's equal to 0. So into my first derivative, which was here, I plug in a 0 everywhere I have a t, and then that's going to be equal to 0. So what that means is negative C1 equals 0. So C1 is just 0. So if it's just 0, then I don't have to plug anything in because 0 doesn't change anything. So that's my first derivative. So now my original function is the antiderivative of my first derivative. So here's my first derivative. So I'm going to take the antiderivative of that, and I get this. Another constant pops up. This is telling me that if I plug in 0 for my c, that it's going to be equal to this. So down here, where was I? Here we go. Plug in 0. Did I say for my c? Plug in 0 for the t. I don't know what I said. Plug in 0 for the t, and then that's going to be equal to this. And so negative c2 equals this, which means c2 is the negative of that. So you have to put a negative 10 in the I, a negative 10 in the j, a negative 10 in the k. So you go back up, where is it? Here, in this step. Go back up here to this step. That was my r. And then I'm plugging in the c2 into that. So notice here in the I, I've added that minus 10, in the j minus 10, in the k minus 10. And I just left this negative out here the whole time. You can distribute that if you want to. I just left it out there. All right, so that's how you do it if you have the first derivative or the second derivative. So in addition to the examples that I've just done, if this is confusing, there's other examples in the book. Let's see. It looks like example 3. So example 3 on page 658 and 659. There's another one. So if you need another example, you can look at that one. Okay, but now let's look at 18. Hold on. 18, it says, a particle traveling in a straight line is located at the point 1, negative 1, 2, and has speed 2 at time t equals 0. The particle moves toward the point 3, 0, 3 with constant acceleration 2i plus j plus k. Find its position vector r of t at time t. So here I have the point. This is the speed when t is 0, moving toward this. And then, where was that problem? Oh, here we go. Constant acceleration is what they call this. So constant acceleration, this is the acceleration, and it's constant because see how here there's no variables? So this is the acceleration. So I want to find r. So this is a problem just like number 16. It's just instead of calling it this, they're calling it a, but a is the second derivative of r, and so it's the same thing. Okay, so the first derivative, which is the velocity, is the integral of the second derivative, which is the acceleration. So I'm integrating this. A constant pops up. And then here they didn't give it to me nice and neat like they did before, so I have to figure it out myself. It travels from this point to this point along a straight line. So it moves along the vector that has this for the initial point and this for the terminal point. So you just do terminal minus initial, and it's moving along this vector. Oh, before I forget, number 6, what type of pet was it? For once, it wasn't my super annoying dog. It was actually my daughter's sugar gliders. She doesn't have them anymore. I would show them to you. She sold them not too long ago, but that's what was making noise in the video that I made this summer. So that was the answer to number 6, my daughter's super cute sugar gliders that I miss terribly, but she didn't want to take care of them anymore, so they're gone. Okay, so here it says that in the original problem, the speed was 2 when t was 0. The speed is the magnitude of the velocity vector. So what that means is when the velocity was 0, that magnitude was 2. And then this is something from, 12.1 maybe, 12.1, that the velocity vector can be broken down into speed times direction. So the speed is 2. And then the direction, remember this vector from the previous page, this vector, direction has to be a unit vector. So you take that vector and make it a unit vector, and then you're multiplying it. So speed times direction, multiply, and you get this. So this vector would be the velocity vector at 0. So this one you had to do a lot of work to find it. So just to recap, because this has kind of been a lot of stuff, they only gave me the speed, and they gave me my starting and stopping point that I'm moving along. So it was a 2-part process. The speed they gave me, the direction I had to find the vector. So I found the vector, which gave me the direction, but because direction has to be a unit vector, I came up here and divided it by its magnitude. And so this is it as a unit vector. So speed times direction, that would be velocity. So velocity is 2 things. The velocity is the derivative of the position function, the r prime, but it's also the speed times the direction. And so if you have speed times direction, you can find velocity that way. So this would be my velocity at 0. And then again, back from this other page, here I just found that the velocity was this. So I'm going to try to find the c now. So this is my velocity. And I wrote it here so we could see it. So what this is telling me is if I plug in 0 for the t, it should be equal to this vector. So go here and plug 0 in for all of these t's, and that should be equal to that vector. Okay, so that's just c1 equals this vector, so that's got to be c1. So you put this with the I, this with the j, this with the k, and that's the velocity. Then the r is the integral of the velocity vector. So I'm integrating what I just found. I get another c that pops up, and it tells me that the r sub 0, not r sub 0, the r of 0. R of 0 is the position at time 0, so the initial position. And so it told me it started at this point, and so the initial position would be the vector that terminates at that point. As you know, position vector starts at the origin and terminates there. So that would be the r of 0. So here's the r, plug in 0 everywhere you have a t, and set it equal to this, so it becomes all of this. And then that would be my C2. So put this with the I, this with the J, this with the K, and I get this. Okay, so unfortunately, in all of my examples, I was always plugging in zeros, so I kept getting zeros, but that's not true in general. In general, you don't have to get, you don't have to be plugging in a 0, and you don't have to get zeros. It just happened that way in all of these examples because this book is very unoriginal, so terribly sorry. Okay, I just realized that there was one more thing on this video sheet that I didn't talk about this time around in this video, and that was number 4. I don't want to go back through and look at my notes to see which one I didn't. Well, I guess I could. Hold on. I don't know. Let's make up something fun to put in number 4. What should we put in number 4? Number 4. Put your middle name. In number 4, put your middle name, just so you know, because that'll be one more thing I learn about you. So number 4, because I don't know what that was talking about in the video I made this summer, and I've already passed out your video sheet, and it's too late to fix it. Write your middle name in number 4. And you can draw me a funny little picture, too, if you want to. If you're bored and want to just doodle a little picture. I don't know, whatever. It's, you know, technology doesn't always work the way you want it to work, so you just got to go with the flow. So number 4, we'll just, whatever, you know, just do whatever you want to do. Okay, so that's all from 12.2. So sorry for the delay in getting it posted and the issues with the video sheet not matching the video because, you know, it is what it is. So anyway, if you have any questions, send me an email.